Hello, everyone. How are you all doing? I hope you're well. Look, guys, I'm streaming from my office where I record videos. Doing a bit of an experiment. My husband and I, we upgraded our internet like earlier this week, so I can actually get a signal out here that's consistent. We're still gonna like run an Ethernet cable out here so I can do real uninterrupted streaming and everything will be happy. But yeah, welcome to my garage office that I like a whole lot. Anywho, so today, nope, I've got to do the YouTuber thing first. Okay, thanks, Secular Rarity. Okay, so my brief. I'm so bad at shilling. I'm so bad at being a YouTuber. Okay, please like, subscribe, all that cool stuff. Also, if you are willing and able to support my science communication habit, there's a buy me a coffee link down in the description. That's all I got for shilling. Cool. We're going to talk about the moon today, and I'm super stoked. Actually, what we're talking about is hydroplate theory, which is weird young Earth creationism thing that I'm going to learn about live, and y'all get to learn about it with me. So we got a series of videos that actually somebody emailed them to me, so you know who you are. Thank you very much. We're gonna check some of them out, and I hope we get to. So why I want to talk about hydroplate theory and where this came from. A few weeks ago, when I debated Kent Hovind, one of the things we started talking about was craters on the moon. I know weirdly a lot about craters on the moon, and part of hydroplate theory is that craters on the moon were formed from rocks from the Earth shooting up and hitting the moon, which is pretty nonsense. And I hope I get to explain why. But let's, oh my goodness, there's like 8 people watching. This makes me so happy. You guys are lovely, and I'm so glad you're here. So let's go ahead. I'm gonna start sharing a Chrome tab. What's up, Harmonica Man? Yes, I am everywhere. Yeah. We're gonna share the audio. Hydroplate theory overview part 1. I think I have skipped over all of the whatchamacallit. I think exactly. Goodness gracious, that was my problem. And I asked Kent about that. And I did get an I don't know from him. So I appreciate that. Anywho, so the first 10 minutes of this 30-minute video were Bible verses. So we skipped over that. I'm trying to get to where he starts talking about the science. I think that's about here. So here he's just been explaining the what the interior structure of the Earth is with our solid nickel iron inner core, our liquid nickel iron outer core, the solid mantle that is made of silica material, and then the crust. Yeah, absolutely. I'm not going to take you on that bet, Zebra, because I'm pretty darn sure this is going to be a fountains of the deep. That phrase is gonna come up. Why do I not have a beer out here with me? That was poor planning on my part. I was going to say I take a drink every time we get that shows up. Okay, cool. Let's play. Let's see what he's got to say. Okay.
The liquid of the outer core is twice the density of the rocky mantle.
Yes.
Zooming in on a cross-section of the surface are made up of finely ground bits of crystalline rock, like granite or basalt, that have been cemented together by a cementing agent like calcium carbonate. For example, sandstone and limestone are sedimentary rocks. Metamorphic rocks occur when sedimentary or crystalline rock is greatly compressed and heated.
He does speak marble and really slowly.
Are metamorphic rocks. The 2 most prominent surface rocks are basalt and granite.
Yeah.
The floors of the ocean basins are primarily lined with basalts, which are igneous, meaning formed from a melt state. We know basalts are igneous because we see them being produced in nature and can replicate basalts from a melt in a lab. Continents are primarily granites, which are slightly less dense than basalts. Contrary to what is commonly assumed, granite does not appear to be igneous, meaning formally melted.
Yeah, so the Earth has a bimodal topography. We have oceanic crust, and then we have continental crust. They are formed in very different ways. Oceanic crust is the easiest to make. You just get some of the mantle, you get some of that, you melt it, and then you let it harden at the surface, and bam, that's oceanic crust. Sorry. Continental crust takes longer. What you've got to do for that is you've got to, usually you have to introduce like water down into the mantle. You make it really slowly. You make it in the mantle. And we also destroy continental crust less quickly. We kind of make and destroy oceanic crust sort of like all the time, and it happens relatively fast compared to continental crust. And there's lots of different processes that are going to make continental crust. I've had one geology class in my entire life, so he may be speaking nonsense, but I actually don't know enough geology to off the cuff, right, dig into what he's saying. Does calcium carbonate absorb, then crystallize in order to hold other rocks in place? Calcium carbonate is cool because it can like precipitate out of a liquid, because that's like what seashells are made of and stuff like that. So you definitely get it in, I think. Oh gosh. Okay. So I don't know the strict answer to that harmonic command, not off the top of my head. So we're getting into geology here. I want to get into more of the geophysics. That's more my jam. And yeah, Zebra, I'm guessing no, but yeah, okay.
Rather than being igneous, granite would be better termed as an enigma.
Granite
is made of very large crystals of quartz, feldspar, hornblende, and mica. These materials have differing densities and melting points.
Yep.
If granite was molten for millions of years and slowly cooled as assumed, the differing liquid mineral densities would naturally self-sort due to gravity, just like oil and water. The result would be a layered cake pattern, not the large interlocked crystalline patterns that we see today.
I see. Okay, so he's misunderstanding how these crystal structures grow, because crystals so as those crystals are growing, right, they're sort of all growing all at once, right? And so it's that we have all of these minerals around, and different minerals tend to form with sort of under different conditions. And then as those crystals grow, so we're if you were to dig down into the mantle and watch some granite be formed, it wouldn't already look like granite does now. So he's kind of assuming that we have all of the parts that make up quartz here, and those are all liquid. And then we have all of the parts that are going to make up the feldspar, and that is all liquid. And then we have all of the parts that are going to make up the mica, right? Instead of, no, these are all you do have to liquefy some of it, right? But these are all forming very slowly, and it's kind of all mixed together, and different crystal structures, which is are going to form under different conditions. I hope that helps. Yeah. So he's misunderstanding how stuff works. So I'm going to skip ahead and not let him talk about rocks. Okay. So now he's going to talk about the continental shelf. Okay. What's going on here?
It's generally thin and taper out under the ocean's surface, forming the continental shelf, which runs out under the water between 300 and 600 feet deep. The true edge of the continent then rapidly drops off in a bevel shape to an ocean depth averaging 12,000 feet, forming the continental slope. Notice that the thinned continental shelf connects the continents. If ocean levels were several hundred feet lower, you could almost walk from Southeast Asia to Australia and from Siberia to Alaska.
Yep, that's true.
If this were the case after the flood, while much of the flood waters remained trapped on the continents, there was a good reason behind God's direction for survivors of the flood to spread out as they increased in population.
Oh, no.
This also may explain why in Genesis 9, Nimrod and those who settled on the plain of Shinar in today's Iraq were quickly confused by God with differing languages and thereby forced to spread out.
Okay.
This also explains after name as a root. This language did the continent from an evolutionary view. There are actually many differing views, but the following appears to be the most popular today.
Okay.
Supposedly 4.5 billion years ago, asteroids gravitationally collapsed into each other.
No, that's not quite right. No, so that's not right. So 4.6 billion years ago, right? Let's go with 4.7 billion years ago. There were no solids in our solar system. Everything was in a gaseous state, and it makes what's called a protoplanetary disk. So you have a disk that is orbiting the protostar, right? And as that star starts to form, it you start to get I'm sorry, I'm distracted by chat. Let me put a pin in protoplanetary disks. And how does the continental shelf tell us anything about the Tower of Babel? Clearly, because people could walk everywhere. I think that's the whole point there. People could have just walked all over the world. Yep, that's special. Okay. So protoplanetary disk. So you have your protostar and everything that will make up the solar system is orbiting it in this sort of well-mixed gaseous cloud, which is called the protoplanetary disk. How do we know this, you ask? Turns out in the sky right now, you can point your telescope at forming solar systems, right? So we can see these stages happening. So that's how we know some of this stuff. And then what happens? So this is all very hot, right? Then things start to cool down. And so as the solar system, the proto-solar system starts to cool down, you get different elements precipitating out of the protoplanetary disk, right? So rocks are the first things to solidify, right? Because they have the highest melt temperature. So it is at the highest temperature compared to, say, like the things that make up like Uranus, right? Like methane and whatnot. So it's the first things that come out of the protoplanetary disk are like rocks. Fun fact, that is why the planets closest to the sun are made of rocks, because those are the first things that precipitated out of the protoplanetary disk. And the further away you get from the star, the colder it is. So the more elements that are only going to be solids at colder temperatures will start to precipitate out further away, etc., so forth. So now you have all these little particles, and they're itty bitty, and they are actually, this is super, super, super cool, which makes me happy. Initially, these are microscopic particles, right? Almost individual atoms precipitating out of the protoplanetary disk. And what you have happening is it's the thing that starts to bind them together, because at this point they're too small for gravity to be a noticeable effect, right? The mass is too small for gravity to be important. Rebecca, yeah, absolutely. Gas giants are always on the outside, which is why the discovery of hot Jupiters is really odd to scientists. So hot Jupiters are exoplanets that are like the size of Jupiter, but are really close to the sun, to their sun. And what we think actually happened is that what we're seeing is orbits. The orbit of those planets, it started further out, but it decayed, and it's like sort of actually kind of ate the inner rocky planets as it moved closer towards the star. So anytime people talk about hot Jupiters are also the easiest exoplanet to find. So we've found disproportionately a lot of them compared to other types of exoplanets because they're really easy to find. But so I imagine hot Jupiters as like giant Pac-Man eating the inner planets. But yeah, so gas giants are generally going to form further away from the star, with rocky planets on the interior. Okay. Yes. Yeah, absolutely. Absolutely. That's how I picture it. You know, that's how my brain works. I just hear the waka waka noise in my head from Pac-Man. Pac-Man is one of the video games I'm very good at. I'm very good at Pac-Man, Super Mario Brothers 3, and original Crash Bandicoot, and that's it. But I'm really good at Pac-Man because my piano teacher had an arcade Pac-Man. And so when my sister had her lesson, I just played Pac-Man for like an hour. Oh my gosh, I am all over the place tonight already. But okay, so we have these little microscopic particles that have come out of our protoplanetary disk, and they're too small. Their masses are too little for gravity to attract these individual particles to each other. So the force that's actually really important are those incredibly weak van der Waals forces. If you guys remember from your like high school chemistry learning about really, really weak van der Waals forces that like nobody thinks are important, but turns out it is for making planets. So it's van der Waals forces and something called Brownian motion. Brownian motion, it just means random. So these guys are randomly moving around and they start to stick together because of this. It's a weak electromagnetic force that starts to hold those little atoms together. They start to stick together. And then once they stick together through that mechanism for a while, then you start to get, once they start to get bigger, then gravity starts to attract these pieces together. And so the trick here is when, you know, things are small and they come together slowly under gravity, then you get gravitational accretion. That is going to be the term we use there. So that is, we take a rock, we smash another rock into it, and we end up with a bigger rock. Problem though, once things start to get really big and they're moving and zipping around the solar system super fast, then what we start to get is we have a real big rock and another rock comes in and smashes into it, and that starts to be a destructive process. So the early solar system is just pieces of rock and ice flying around, smashing into each other, right? Sometimes getting bigger, sometimes breaking up. And so you have to have sort of, they need to get accretion, you sort of need to have, I think both objects need to be about the same size, and so they can like smash together and then be held together under the gravity of this new system of all the bits. Naboo is an impossible planet, even if it was engineered. I don't know which. What's the order? I do know that Naboo is a Star Wars planet, right? But I can't. So I know what you're talking about, but I can't remember what order it is in the solar system. And I don't remember. But anyway. So, Don Giovanni, if you'll remind me on that. Things. Yes. Cool. Okay. Okay. Yeah. So first we have things that come together under like gravity, and then you get, first we have things that come together under van der Waals forces and Brownian motion, then it's gravitational attraction. And again, it's sort of the composition of what planets are doing is a function of distance from the sun. So Jupiter is where it is because that's where like our hydrogen and hydrogen compounds were going to be able to come out of that protoplanetary disk, and accrete under gravity. What's actually something that's really cool about both Jupiter and Saturn is we don't actually know if it's just gas all the way down or if there's some rocky core right at the center of that Tootsie Pop. So we don't know. So that's actually kind of really cool. And then, so then you get the gas giants, and then you get these ice giants further out. That's like Uranus and Neptune. And then this is actually really cool. There's at a point when the star, I don't exactly know what this force is, but it's sort of, the best analogy I can think of is the star of this like forming solar system almost exhales, right? And there's a sweeping force that goes through the solar system and it pushes the remaining bits of debris. Also, hi Dapper. The remaining bits of like pieces that didn't quite make it into planets, it pushes them out. And so that is why we have the Kuiper belt. So the Kuiper belt, if you did not know, is the bits of comets and asteroids that are past the orbits of Neptune and Pluto. And that's actually what Pluto is. Pluto is a Kuiper belt object. It is a leftover thing that didn't quite make it into a planet. So it's a dwarf planet. Yeah, that's what we call it. Sorry, I can only think of protoplanet for whatever reason. So yes, that's what's going on. So you get all of these debris sort of get pushed out. This, I think, corresponds with what's called the late heavy bombardment, which was 4.2 billion years ago. So what is the late heavy bombardment? The late heavy bombardment was sort of the last period of time where just asteroids were zipping around, making impact craters on everything. So you might have noticed if you look up at the moon or you look at Mars or Mercury, they both are just covered. Their surfaces are covered in craters. And Earth, less so. We know that Earth recycles its crust, right? So we know that there used to be lots and lots and lots of asteroids making lots and lots and lots of craters. And now they are less common. It turns out there was a pretty sharp break where asteroid impacts were incredibly common up to 4.2 billion years ago. And that period that's called the late heavy bombardment. And after that, they are no longer common. These are fairly rare events. Oh my gosh. I have all my solar system formation knowledge is coming out today. This is fun. I don't get to talk about this stuff very much. Okay. Okay, so that's how the solar system formed in, 5 minutes or less. Let's see what this gentleman, what he says is how it formed. Okay, let's let this play.
And the energy released from these impacts produced a molten liquid Earth,
nope,
which remained molten for millions of years.
No?
As accretion ceased.
No. Oh my goodness. No. Okay, so Earth did used to be molten in its past. That's absolutely true. But it's not because of like impacts. It's not like we had a solid Earth and then we chucked it with rocks and it became molten. No, it's if you take the mass of the Earth, right? And you assume, if you take the mass of the Earth and you're like, okay, well, all of these bits used to not be in one planet, so they used to be far apart. So if you just bring the mass of the Earth together under gravity with no other energy, right? It's just like, boop. Well, yes, what he was saying was nonsense. So if you just bring all of the bits of the Earth, all of its mass together under gravity, that's enough energy to completely melt the Earth. We also know that the Earth used to be molten because we are a fully differentiated body. What is a fully differentiated body, you ask? Great question. That is all of the heavy bits, the iron and nickel, sank to the core, right? And then if you slice through the earth, it's sorted by density. We have iron nickel core, the lighter silica floating on top. And again, you get that just by bringing together Earth's mass under gravity. Okay, now I'm going to try to let him talk for longer than 2 seconds.
The surface eventually cooled and formed a solid crust. But as we just covered, a granite crust could not have originated from a previously molten condition. And no lab has ever been able to replicate granite from a molten state.
So, right. So, because you would start with like a basaltic crust and then make continental crust over a longer period of time. Basalt you can make like that, right? If anybody happens to be in Iceland, they're making a lot of basalt rock right this minute with the volcano, right? You can, a human can watch that crust happen. Making continental crust is harder, and it takes longer periods of time, but that's fine.
The evolutionary model then states that over time, the remaining inner molten materials were gravitationally separated to form the dense, solid inner and outer cores of the Earth. Note that any thermal analysis accounting for all realistic forms of heat generation and heat transfer predicts that the sphere of Earth should have completely solidified by now if it is actually 4.5 billion years old. This is one of many observations which strongly indicate the upper limit of Earth's.
So here's a problem with that. So he's saying that our core that liquid outer core should be, whatchamacallit, solid by now. Except that, so like there's a reason we have a liquid outer core and then a solid inner core, right? And that's because of like pressure, right? So temperatures and pressures matter. Right. So like, because the inner core is solid because it's under more pressure from, the weight of the Earth above it. And then the outer core is liquid because that temperature. So I think what he's referring to when he says that like all possible calculations imply that the Earth should have like cooled to the point that it's completely solid by now. I actually think he's referring to just cooling by conduction, which just doesn't work. There's other processes going on. And believe it or not, energy is still added to the Earth system. You have to take into account radioactive decay of material in the mantle. So that claim he just made, like, I don't know the exact source off the top of my head of why it's wrong, but I'm very sus of that. And he doesn't give a source. So, like, my guy, if you don't give us a source, then, like, you might as well say that the sky is made of Smurfs. Because without a source, it just doesn't, right? Something like that doesn't matter. If you want a source, by the way, for all that nonsense I was spotting earlier, not nonsense, but like solar system formation, I've got a really great textbook behind me. No, that's the wrong textbook. Shoot. I don't have this one. It's at my, love that burn. Marie Curie is like one of my favorite scientists. She's who I want to be when I grow up. Sorry, I have this great textbook, but it's at my office and it just looks suspiciously like my atmospheric science textbook that's right there. But there's OCW. Do y'all know what OCW is? MIT puts almost all of their coursework, all of their classes, like up online for free for anybody. So my solar system rant there was from when I took 12002 as an undergrad, which is physics and chemistry of the terrestrial planets. And you can find that on OCW. I can pull that up really fast and like drop a link to where you can get like all of the same lecture material I got to listen to when I was an undergrad. OCW.mit.edu. I'm going to let him talk while I pull up that link. So we'll see what else he has to say.
Age is much younger than assumed when relying on radiometric ratios.
That's false.
To further investigate the fundamental problems with radiometric dating, please refer to my other video titled Hydroplate Theory, The Origin of Earth's Radioactivity.
I believe we will.
Evolutionary
just not
theory
tonight.
of the Earth's origin assumes that the Earth remained in a molten state for around 200 million years. Naturally, any water brought by asteroids would rise to the surface and evaporate long before the Earth's crust solidified. A runaway greenhouse would have followed, trapping solar heat in the humid atmosphere and making life on Earth impossible forever.
Okay.
According to some evolutionists, millions of years after surface solidification, comets bombarded the Earth, depositing even more water on its surface. But recent discoveries of high deuterium concentration, or heavy water, on comets, compared to Earth's oceans, have led some scientists to conclude that Earth's water could not have come from comets. In summary, the evolutionary theories of how water came to be so prevalent on Earth's surface is not supported by what we observe today. But if we assume the evolutionary theory is somehow true, then basic scientific principles tell us that Earth's water should only be found on the surface. What is surprising from this evolutionary view is that there are unexpectedly large amounts of water trapped at depths far deeper than surface water could ever seep. Here is why deep water under continents is not expected. Imagine a block of soft modeling clay or Play-Doh. Now stack more blocks of clay on top. Eventually, the bottom block will deform sideways due to the weight of the added blocks. Add more blocks and more of the material deforms. Now imagine that you have stacked another column of clay blocks very close to the original column. What will it do? It too will deform and compress against the other material. The dashed line represents the boundary at which the compressive strength of the clay or Play-Doh has been exceeded. Material below this boundary forms a tight seal. Even small microscopic cracks cannot exist below this boundary line. Take notice that gravity is the causal source of this condition. Even if surface water is poured into the gap or crack, it cannot seep below the boundary line. For clay or Play-Doh, this boundary may be only a few feet from the surface. You've likely seen a similar scenario after making stovetop pudding or cheesecake, after it cools in the refrigerator overnight. The semi-solid separates or cracks at the surface as it cools, but the crack is not very deep because the weight of the material slumps and closes the crack at a certain depth. Rock like granite has good compressive strength and can support a crack of up to 5 miles depth, but no deeper. In summary, assuming the evolution scenario, water from...
I'm legitimately struggling to understand what this guy is trying to say. Like, we don't expect to have lots of water under, like, not on Earth's surface. Correct. Cool. Is this true, the compression strength thing? I'm not gonna lie, I was kind of only half listening because I was digging up that source, but for whatever reason, StreamYards isn't letting me, it's not letting me edit the description live, so I'll just add that after the broadcast is over. Oh, wait, shoot, I'll put the link here. There you go. There's a link to, in the chat, to OCW, Open Courseware course on how the solar system formed. So yeah, I mean, like, compression, I mean, if you put lots of things on top of each other, right, the weight, it'll start to compress. I think that's all he's trying to say. The structural integrity of the layer at the bottom will eventually give way. Anywho, okay, let's, so no, we don't expect to have lots of water underneath Earth's surface. That's fine.
Asteroids and comets collected on the surface before crust solidification, since granite's max compressive strength is approximately 23,000 pounds per square inch. No significant continental water would be expected below 5 miles depth. However, it is well known that deep water exists much deeper than this. Germany's KTB dig and Russia's Kola dig are the deepest man-made holes in Earth's crystalline continental granite.
Cool.
The goal of these digs was...
It is important to note that not all of continental crust is granite. Like, it's other stuff too. Okay.
To reach the Earth's mantle rock, but neither succeeded. Both holes reached depths well below the 5-mile boundary of granite's mass.
Okay, sorry, I don't. Oh, good. He's saying water is going to come up from beneath. Okay, no, we've got to listen to this.
Increased. Even more surprisingly, they both struck saltwater-filled interconnected fractures in the granite. More recently, using conductivity measurements, a mile-thick layer of saltwater-filled sediments has been reported 10 miles under the Tibetan Plateau. In fact, deep saltwater appears to be a common
Okay, so this seems a little silly, but I'm actually struggling to sort of understand what he means by like deep, because if we're talking about like the structure of the earth, if the earth were the size of an egg, the crust would be like thinner than an eggshell, right? So if we're talking about like the whole earth, 10 miles isn't deep. But he's trying to, it's in the crust too, so I don't expect there to be any water in the mantle unless we specifically like bring it from the crust, like from the surface down into the mantle. That does happen when you have like an oceanic plate subducting under a continental plate. As it's going down, it brings water with it. That introduction of water is really important for continental crust formation processes. But I don't know what this guy's point is. I really don't. Okay.
Trade under all continents. Hydroplate theory asks the question, if evolution theory does not predict deep water, then how else did the water get so deep under?
Honestly, my gut here is just is going to be, we know there are processes that bring water down, right? Like because compressive strength, density, gravity, it's not permeable to water because all the cracks close. So I mean, like, but you don't have to bring water. That makes sense. Like, thank you for that summary. But like, again, you can bring water into the mantle when you have subducting ocean crust. So like, you can take water from the ocean and bring it under a continent, right? That's just my so for the question, how did water get so deep? That's my gut answer is plate tectonics, is we moved it there when we were destroying ocean crust and making continental crust. I don't know that like absolutely for certain, but that would be, if I was sitting in a class and a professor asked me this question, I would raise my hand and throw that out and, maybe get shot down, but or corrected or whatever have you. Okay, so cool. They're gonna say the Bible says God put it there. We're just gonna skip. All right, hydroplate theory, team. Hydroplate theory. It sounds so scientific, and it's gonna be such nonsense, and I'm here for it. I'm stoked. Okay.
The observations we've just covered to derive its starting assumption about the original layout of Earth, which is radically different than what we see today, and certainly much different than what uniformitarian theory proposes.
I had to learn this. Uniformitarianism was like a one that was not a phrase I had ever heard before I started watching young Earth creationist videos. And it's not a modern scientific thinking. It was a like school of a thought amongst, I think, yes, exactly, Don. In like the 1800s, I think, amongst some geologists, but it's uniformitarianism isn't like a real word these days. I'm very fidgety today, guys. So this is also my sewing room, so I've got embroidery hoops and things around. So don't mind me if I'm fidgety. Okay. Let's let him chat. What do you got to say, good
sir? The Earth's surface crust was formed above a deep layer of water. Okay. This is a global condition wherein the Earth crust was an unbroken spherical supercontinent which covered and sealed in a deep layer of water trapped between it and the mantle rock. Many imagine that a combination of forces like the tidal pull of the moon, Coriolis forces, and centrifugal forces would somehow rip this shell apart immediately, and therefore hydroplate theory is invalid from its first assumption. However, few can maintain such a view once they compare all these forces to the dominating gravitational force of Earth. Although other forces are present, they can often be ignored because they are so small compared to gravity. There is a reason gravity is the first force we learn of in school. As we discuss the hydroplate theory's many observations, take note of how so much of the theory's explanation is simply founded upon the physics of what happens to materials under the influence of Earth's gravity. Rather than speculate.
I think this is going to be silly. So, right, let's just think, water is a thing. It flows, it moves, liquid water especially. So you'll have to excuse me if I'm like, no, tidal pull of the moon, very important, right? We know that moves, right? That makes things move. It's feet, 10 feet easily. And that's incredibly destructive. It certainly can be incredibly destructive. Sorry, I was thinking about storm surges with hurricanes, because we're approaching hurricane season. And also, today was my last day of class in my tropical meteorology class, and we were talking about hurricanes and typhoons and other things. So I've been thinking about storm surges, which is like the force of the storm on top of the normal tide. And then it's like, oh no, that's how things get destroyed in coastal areas. But yeah, so like the oceans are being held to Earth by the moon, by gravity, and are also affected by the moon, right? So, my guy, you can't, and like Coriolis is a real thing. That would, unless you're trying to imply that this imaginary layer of water would be like completely stationary, which I don't know how you would suggest that. Yeah, I don't know how you would get that. Okay. Let's see what you got to say.
Unconfirmed natural processes or imagined miracles. We'll see hydroplate theory turn again and again to Earth's gravity as the causal mechanism which drove processes and produced various effects. The Bible records.
I'm also just, if you think that the Earth was formed by like asteroids hitting an already formed Earth, which is sort of what you said earlier in this video, then I really don't think you understand gravity.
Further detail of these assumed starting conditions in the creation account of Genesis 1. The Hebrew for waters here is Mayim. In verse 2, to clouds and vapor said, let there be an expansion. It comes from the root word mean a plate structure. The term real. Again,
I like how he was just like, we're gonna like just talk about science here and not rely on scripture. We don't need to rely on miracles. And yet, first thing we're doing is quoting some scripture and talking about Hebrew words. So that's inconsistent. Yeah, also, right, like, also, the Earth isn't a perfect sphere, right? We do bulge at the equator. So you would get that bulge too. So that seems strange. That seems strange to me, how you would get this. Okay.
Genesis 1 verse 2 were divided in half and has never been formation of the third day will expanse and bring expanse was.
Oh my goodness. Okay. You got to start talking about science, man. Pillars of the deep. Ooh, we haven't quite gotten fountains of the deep. Okay, here we go.
Landmass with many small, shallow seas dotting the surface. Mountains would have been smaller than today. Hydroplate theory figures that approximately half of the water in today's ocean started out under the granite of water found in the Bavarian KTP dig hole. Okay. In addition, water found in comets contains around twice the deuterium concentration that is in the oceans. The estimate also assumes that pre-flood seas were freshwater, which after the flood mixed about equal parts with this super salty, deuterium-rich subterranean water, diluting it to the levels measured in the oceans today. I will describe more about the most likely origin of comets later, so hold on to this info, as I'm sure at this point it seems strange that water and comets would have anything to do with the flood or with the Earth. Hydroplate does not place an upper bound on the original volume of water in the chamber because there are some unknowns that have a large effect on the final answer. Today we know there are large amounts of water trapped deep in the porous Mohorovičić boundary layers, but we don't know by volume how much is down there. We also don't know how much water escaped Earth's atmosphere during the flood. Both of these unknown variables would add to the volume estimate based on the above concentrations of deuterium and salt. So for now, we'll just say the deep, or the Great Deep as referred to in Genesis 7.
Sorry, that was like, I was legitimately trying to understand what he was saying. And I wasn't really following. But yes, magic. They got there by magic. So, yeah. Deep water mixing with the top. I don't. This is. Oh my goodness. Okay, let me try. I'm gonna try to follow.
11 was a global interconnected subcrustal ocean chamber that was at least 0.9 miles deep at the time of the flood. Based on observations of current size and thickness of continents, hydroplate theory proposes that the original granite plate was 60 miles thick. If you've read prior editions of the theory, you'll notice that this has increased from initial estimates of 10 miles thickness.
Okay, that's fine.
This change was arrived at after carefully in New Zealand waves to produce the clearest picture of what they...
Seismic reflection image for the base of a tectonic plate. The slippery base of a tectonic plate. Those actually sound like fun papers to read. I do appreciate that he cited some papers. So tectonic plates, by the way, are super cool, right? Because they just they are effectively floating on top of the mantle, and they just slip around. One of the things that I think is being missed here, but like. This is kind of a problem for young Earth creationists, right? Because the mantle is a solid. If we could dig down and look at it, it would be a solid, right? But it also convects on geologic timescales. So you get this solid that is convecting, which is very cool. But you have to wait a very long period of time, like tens of thousands to hundreds of thousands of years. So like, I don't know how that fits in young Earth creationism. If we're only 6,000 years old, you know what I mean? How do we have a convecting mantle? So like, how do we have a magnetic field, right? If there hasn't been time to get that convection going, I don't know. That seems like a difficult thing to explain, but okay. Okay. Back to it. We're going to listen.
They believe to be a subducting plate. They are puzzled, however, because almost 50 miles down, a 6-mile thick channel containing melted rock and or water has also been identified. This is not at all what popular plate tectonic theory predicts. For hydroplate theory, these discoveries are exciting because they are consistent with how a collapsed water-permeated subterranean chamber would be expected to reflect these seismic waves. The much slower wave velocities measured in the channel indicate magma and or water trapped within the chamber's roof and floor.
So it's not uncommon to find like they're not puzzled. They cite another paper. I'm so happy that that's the answer. Oh my goodness. Because it wouldn't be odd. It wouldn't be odd that to find a pocket of like liquid magma, especially where you have a subducting plate. That's an expected thing in that type of location because that's where you kind of need magma to make new crust, to make new continental crust. So I don't. Yeah, I'm glad you found that paper. But like when he says they were confused, my gut reaction there was I don't believe you. Like I really don't believe you that they were confused. Uh, uh, I think maybe they found something they like weren't strictly expecting to find, but there are known natural processes for how you would get that thing, right? This isn't hard. This isn't scary.
We will soon cover in detail how hydroplate theory explains these findings using cause to effect reasoning. This is the first strong evidence that
I've been listening to this guy for almost an hour, Don, and your conclusion makes as much sense to me as his does. So fair. Okay.
That the granite crust was in fact much thicker than previous estimates. Corroborating this is the growing body of evidence that trans-Neptunian objects, or TNOs, are most likely from Earth as well.
TNOs? I think they made that up. Trans-Neptunian objects. So that's the Kuiper Belt is what he's talking about, by the way. We mentioned that earlier. Why would we think those came from planet Earth? That doesn't make any sense. I want to know about that. Where oh my goodness, you can't just throw that out there, my guy.
We'll discuss this further later on. For now, we'll continue discussing the assumed initial pre-flood conditions.
Okay.
Remember, no cracks can exist in granite below 5 miles.
Why?
So the perfect seal conditions we just reviewed existed to keep the surface waters from seeping down and, more importantly, the subsurface waters of the deep from pushing up through the granite. These are the basic starting assumptions of the hydroplate theory. From here, the theory uses only laws of physics to explain cause to effect, which we'll see provides reasonable and straightforward explanation of Earth's surface features today. This is a phase diagram for water.
I thought that's what this was going to be.
At atmospheric conditions, we see water freeze at 32 degrees Fahrenheit, 14.7 pounds per square inch pressure. As heat is added, ice melts and the temperature rises until at 212 degrees Fahrenheit, boiling produces vapor.
That's at...
The weight of 60 miles of granite above means that the Great Deep was pressurized to approximately 370.
This is yeah, so good. He's going to talk about this, but the temperature, what phase, whether something is a solid, liquid, or gas, is a function of both temperature and pressure. So, you got to talk about that. I keep clicking the wrong thing. There we go.
2,000 pounds per square inch. As will be seen, work was being done on the water of the Great Deep, which gradually increased its internal energy. So we will refer back to this diagram several times and see how conditions in the water changed and the dramatic effects that were produced.
Cool.
Just as the moon's gravity works to produce the ocean tides, the original granite shell would also have been worked and distorted by the moon's gravity. However, because it was a solid shell of great mass, the tidal effect on the crust was not as dramatic as with the open sea. Still, the crust would have deformed into a slight egg shape toward the moon. Obviously, the graphic has been exaggerated so we can see the distortions, and I've simplified the pillars to only 4 dark brown shapes, where the granite was pressed into the solid mantle. In reality, the global surface area of the relatively thin 60-mile crust would have allowed it to form pillars at thousands of locations. Twice a day, the shell would have deformed, so the trapped waters of the deep were continually being pumped through the subterranean chamber at high pressure. This work added energy in the form of heat.
What? What? So we're pumping this water around? Yeah, that's gonna do a lot, man. I don't know what to say about this. I was not expecting this. Oh my goodness. No. Okay.
The waters under the crust. At the same time, each pillar experienced tension, compression, and shear loads twice a day. Friction from these cyclic loads slowly heated the pillars as well. To get an idea of how these forces produced heat, bend a steel wire or a paper clip back and forth several times, then touch it at the bend. Now imagine how much heat would be generated at the extreme pressures in rock 60 miles deep.
That's a problem. That's a problem for you, my guy. Yeah, I'm kind of at blue screen of death here, guys. This is, oh my goodness. Okay. We're gonna do it. We're gonna do it. Okay.
As tidal pumping continued, the pressure and temperature in the subterranean chamber increased. Eventually, liquid water phased into a state known as supercritical water. The hydroplate theory is not the first to recognize the possibility of a supercontinent. We all learned about...
No, stop right there, good sir, because we just went to supercritical water, full stop. First of all, what does that mean? I don't. And then we're just like, also, look, Pangaea existed. Humana. Okay, we're going to finish this, and then we're going to look at a phase diagram. Goodness.
About Edward Bullard's Pangaea concept in high school. Few of us were encouraged to look at it critically, however. For example, what happened to half of Mexico and Central America? And what forces rotated North America clockwise, while South America was rotated counterclockwise?
Plate tectonics, dude.
We also probably did not catch the fact that Africa's area is actually 35% larger than we were shown in the books. That's right, Africa had to be scaled down by about 35% to make it fit the picture. In fact, Africa and Europe fit poorly.
I cannot stand this idea that, like, something presented in a textbook for children is not 100% perfectly accurate, because we had to explain it at a level for children, right? So like I don't want to just use the phrase dumbed down, but like, if you're teaching a second grader, you're not going to start with general relativity, right? Like, you're going to teach things at the level the audience can understand. So, like, of course, and you hear younger creationists do this all the time, where it's like, oh my gosh, this textbook for children isn't perfectly accurate, so we're just gonna like attack those things. It's like, but it's for a child. Like, if you want the like most up to date, most accurate science, like, you've got to go to the peer reviewed literature. Anywho, okay, we'll let him keep going.
With the Americas when positioned in 3D on a globe.
I hate to break it to you, my guy. I know I went for 2 seconds, but erosion happens. Like those plates, the continents as they are today is not the same. It's not the same landmass that existed at the time of Pangaea. Because that was what, oh my gosh, I don't want to just say this off the top of my head, but I think 500 million years ago? A very long time ago.
Especially when you include the continental shelves that extend under the oceans and do not allow removal of materials as needed in order to force a fit. There's another feature on the globe that fits these coastlines much better. One of the key observations Walt Brown has made is that with an actual 3D globe, the coastlines of all four continents fit very well with the mid-oceanic ridge.
Well, yeah. Because that's how plate tectonics work. Like, okay.
Discovered in the 1950s, which wraps around the rim of a bay, the longest mountain chain at 46,000 miles length. The fact that this is almost entirely covered by water is not the only trait that sets it apart from today's continental surface mountains. As we'll soon see, the mid-oceanic ridge is a scar in Earth's mantle left over from the flood, which roughly traces the path of the crack that opened up in the granite shell.
No.
Surface mountains appear to be the result of compressed materials that have been piled up. This makes sense. Push compressed material together and it piles up. But the mountains of the mid-oceanic ridge are uniquely different than surface mountains. Tensile fractures show that the material has been pulled apart in two perpendicular.
Yes, dude, because these are oceanic plates that are moving apart. They're going like this. They're going like this. A new oceanic crust is forming underneath them, and it's pushing apart, and then the edges are subducting under the continental plates at the other end.
Other directions. This is counterintuitive. How do you build a mountain chain by pulling material apart in two directions, no less? Hydroplate theory explains the unique conditions that produced this.
I think it's because as they spread, as you get this ocean floor spreading, it's new crust is formed, right? So it spreads apart, new crust, new liquid magma comes up, solidifies, moves, right? So kind of the same way that you make Hawaii.
Strange global geologic feature.
It's not that odd. We'll discuss how
this happened later, but first let's continue to investigate the nature of supercritical fluids, since it is key to understanding and grasping the magnitude and direction of energy released during the flood.
Okay, and that is the end of this video. Great. Let's talk about supercritical fluids for a second. Yeah, so I'm going to stop sharing that, and I'm going to share screen. I'm going to share this window. Nailed it. Okay, and I'll make myself little so you can see what I'm Googling. Okay. All right, let's just go for supercritical CRITICAL fluid. Supercritical fluid. Bam, bam, bam. Substance at a temperature and pressure above its critical point where distinct liquid and gas phases do not exist. Oh, okay. But below the pressure required to compress it into a solid. Oh, okay. That's fine. Cool. So yeah, on our phase diagram, which is going to be this sucker, it's, oh, okay. So I think what's going on there, yeah. Okay, sorry, I know what this is. Sometimes when I watch young Earth creationism videos, my brain breaks a little bit in the meantime. Basically think of it like this. If you're in the supercritical regime, if you were to look at any one atom of water in that regime, it's equally likely to be a liquid or a gas. Right, because Pangaea is totally the only one. Yeah. Okay, that's all. Okay. Oh goodness. Yeah, it's equally likely to be a liquid or a gas. I don't know why that's going to be important for his hydroplate theory thing. I don't know. Okay. I thought we were possibly going to get to the moon, so I did cool pictures pulled up. I think I don't have another full video in me tonight, guys. I think we'll do his overview part 2 next, same bat time, same bat channel next week. But I have some pretty pictures of the moon I wanted to share with you because you guys are very cool. So that's okay. So I didn't want to start with Grail. I wanted to start here. This, guys, this is a topographic map of the moon. And it is made from data from NASA. The instrument is called LOLA. That's Lunar Orbital Laser Altimeter. And LOLA is very near and dear to my heart because I got to help make this when I was an undergrad. And that's why I know an obscene amount of things about impact craters, because I looked at a lot of them and I mapped them and I measured them. And Yeah, so this is Lola. This is Lola data and our topographic map of the moon. So what you're looking at straight on there, that the center of the map is the near side of the moon. So it's just kind of flattened out, right? And then on the edges where it gets much bumpier and higher topography, that is, those are the highlands. That's the far side of the moon. And what I wanted to show you guys, because this came up with my debate with Kent Hovind, was, so my question to him was, if all the craters on the moon were caused by rocks flying off of Earth and getting shot into space and hitting the moon, then why is the near side of the moon less heavily cratered than the far side, right? Wouldn't you expect that to be the opposite if with this like hydroplate, whatever have you ness, where we just shoot things into space? Yeah. So, and then he asked me a question that I didn't have an answer to, which is, oh, so why are the mare, those flat regions on, flat dark regions on the near side of the moon, the part we can see, why are those only on the near side? Because those are large impact events. And those are the results of large impact events, which caused melts and the forming of basalt material. And they are less heavily cratered than the highlands and the rest of the moon. And I didn't actually have a good answer for that. And so I did a little reading in the meantime. And the short answer is because the moon's gravity is weird. So this sucker is a map from, this is a map of the moon's gravity. It's not the same map projection as what I just showed you. So do you see this 0 degrees here? 0 degrees, the prime meridian of the moon is right here. So the gravity map sort of starts and goes this way and then connects and loops around. So I couldn't find a topographic map and a gravity map on the same grid. So I just wanted to point that out. So the main thing to notice here is that, so notice we've got these like big red, so gravity here is like anomalously strong, and gravity in the blue regions is anomalously weak, right? So we have, excuse me, and it's just kind of a little all over the place, right? We have, especially on the far side, these are actually where you have all these red anomalies here. That's opposite the mare. That was something that this mission was interested in studying. But the main, there's a lot of things to look at. By the way, this comes from the GRAIL mission, GRAIL. That was also NASA Goddard. The main point here that I actually just want to point out is the swings are like -500 to 500, right? And the units there are like milligal, which is an odd unit. But for comparison, here is a gravity anomaly map of the Earth, right? And check out this color scale, right? It only goes, our gravity anomalies, it's the same units, but only go to -120 to +120, whereas the moons swing from -500 to 500. So it's like it's almost 10 times the swing, right? All of that to say, moon's gravity, real weird. Anywho. Yeah, ice ages, they're periodic, which is really cool. Yeah, and he's just going to talk about like the one ice age and give it, a brief period of time. Anywho, that is the gravity stuff I wanted to share with you guys. I I want to thank you guys so much for hanging out with me. I'm going to stop sharing that I don't have another Hydroplate video in me tonight. I'm so sorry, team. There's part of me that kind of just wants to power through, but I went full blue screen of death on my brain. And yeah, thank you. Yeah, so I am gonna say good night. Have good evening, team. I'll talk to you guys soon. All right, good night.